Well, hi everyone. Thank you so much for coming to this IAP short course on the fundamentals of climate science and policy. We're super excited to put this course on for you and hopefully teach you some of the important things you need to know about climate change and the problems that the world is facing right now. I just want to give a quick shout out to the course organizers. We have a group of grad students that have taken the time to put together this course, and they'll be introducing themselves as they get up to talk. And then I also want to give a shout out to Monica, who I think might have just walked out, but she's been helping us organize a lot of the logistics for this course and has done a great job and been super helpful. So just, if you see her, say thank you, because this course would not have been possible without her. So just to give a quick overview of the week, today we'll do an introduction to climate science, look at some of the fundamentals that you need to understand whenever you're thinking about climate change. And then we will also do a quick introduction to the basics of climate policy. Tomorrow we'll dig a bit more into the details. We'll look at climate change impacts, the uncertainty, and the extent to which climate change is reversible. And then we'll also take a deeper dive into some of the theory around economics as it relates to climate change and look at some examples of environmental policies. And then finally on Thursday, we will have two fun activities for you. We'll have an interactive session where you can get some hands-on experience for what it's like to develop climate policy. And then we will conclude with a panel discussion where we'll have 3 people working here in Massachusetts on issues related to climate change and the economics surrounding climate change. So you'll be able to ask them your questions and get their input on things. Just to set some brief expectations, so during the talks we ask that if you have any clarifying questions, you can raise your hands or raise your name tag and we can answer those for you. Please hold all other questions to the end. We'll have some Q&A time scheduled at the end of the session, and we'll bring a microphone to you so that everyone in the room is able to hear the question. And then lastly, the name tags and the tents are for all 3 days, so just be sure to leave them at the end so that they're here for you tomorrow and on Thursday. So we'll get started with it. This first presentation is just going to be on the basics of climate and what climate science is, or how we can understand the basics of climate science. Myself, I'm Paul Nicknish. I'm a grad student in the Earth, Atmospheric, and Planetary Science department here at MIT, and I work on questions related to how the hydrologic cycle will change with climate change.
Hi, my name is Eric. I'm a fourth-year PhD student in the Department of Department of Earth, Atmospheric, and Planetary Sciences, and I study atmospheric chemistry.
Hi everyone, I'm Sandeep Chinta. I'm a postdoc at Center for Sustainability Science and Strategy. I work with weather and climate models, machine learning, and I mostly work with extreme event risk and how it impacts human societies.
Cool. So just to give you a quick sense of where we're going today, we'll first look at the concept of energy balance and how this relates to setting a planet's temperature. Then we'll take a closer look at the atmosphere of Earth and look at how the various constituents of the atmosphere modify the climate system. And then finally, we'll look at potential sources of internal variability in the climate and how these compare to the rates of warming that we've seen recently, and see if we can try and better understand what's human-caused and what's natural-caused. So the reason that we're all here is because the world is getting warmer. The World Meteorological Organization estimates that there's been roughly 1.3 to 1.4 degrees Celsius, or 2.4 to 2.5 degrees Fahrenheit, of warming relative to an 1850 to 1900 threshold. And if you look at the last 10 years, these 10 years constitute the 10 warmest years on record. And so there's no doubt that we have a warming planet, and part of the challenge with climate science then is to understand what are the impacts of this warming. How is it going to impact human society? How is it going to impact the systems that we've put in place to keep society functioning? But before we get to that, we need to first just answer the basic question of what is climate. We're interested in questions related to climate change, and whenever you're talking about climate change, it's important to keep in mind what exactly you're talking about. There are many famous sayings out there that sort of encapsulate this, and perhaps one of the most famous comes from Mark Twain, and it goes, "Climate is what we expect, whereas weather is what we get." In other words, you can think of weather as sort of this noisy, varying system. The temperature can change a lot from one day to the next, but climate is going to be the average of those weather fluctuations over long time scales. Said another way, climate is just the statistics of weather, and I think this can be visualized nicely with the schematic here, where you have a dog that's sort of running erratically around, up and down, and you can think of the dog's path as being analogous to what the weather system is doing. And then the person who's walking the dog has a much smoother path that reflects the average motions of the dog. And so this is the climate system in this analogy. So we're interested in questions about the climate. We want to understand why the climate is changing. And if you look on the Earth on any given day, one of the first things that stands out is just how much is happening. There's a lot going on that is going to impact the climate system. You have clouds that have all of these structures in different length scales. You have continents that have rainforests and mountains and deserts. And then you have oceans that cover 70% of the Earth and are supplying moisture to the atmosphere and are moving heat around on the planet. So you have a ton of things going on. And at first it can seem borderline overwhelming to try and model and understand everything that's happening in this picture here. The Earth is so big and complicated that we aren't able to run traditional laboratory scale controlled experiments on the planet. And so the way we learn anything about a system as rich and complex as this is through using models. And when I say a model, I just mean a set of equations that tries to encapsulate, or traditionally I mean a set of equations that tries to encapsulate the physics that is driving a system like this. So there's a lot going on here, and we'll talk about full-blown Earth system models that try to do exactly that, represent this picture here. But for now, we're going to consider something much simpler to try and gain some intuition for how the climate works. And at this point, I want to mention the concept of energy balance. Energy balance is just the idea of tracking energy fluxes in and out of a planet, and this is going to be fundamental for understanding a planet's temperature. So let's start with this simple setup here. We have a star, much like our own sun, that's emitting radiation, we'll call solar radiation. And then we have a rock, much like Earth, but with no atmosphere and ocean, and this rocky planet is orbiting around the sun. And one of the key things about this planet is that it'll be emitting outgoing or terrestrial radiation. And this terrestrial radiation is going to be proportional to some effective temperature of the planet raised to the 4th power. It's a black body radiation, if that means anything to you. And so if you consider that the planet to be an energy balance, in other words, the energy coming in is equal to the energy going out, then you can use the fact that the outgoing energy is proportional to temperature to back out what the temperature of the planet will be. And if you do this calculation for reasonable parameters of the sun and using the Earth-Sun distance, you get a temperature of minus 18 degrees Celsius, which is extremely cold, much colder than the average temperature on Earth today. And so it suggests that there has to be something else going on Earth that's keeping us much warmer than would be suggested from this simple model that I've gotten here. So we're going to take one step up in complexity, and we're not going to fully jump to the full Earth, but instead we're going to consider what we call a box model and have 3 different boxes. One that models or encapsulates what's happening in the atmosphere, one for the land, and one for the ocean. And again, we have our incoming and outgoing radiation from this slightly more complicated planet. It turns out, for understanding the energy balance, one of the key control on this outgoing radiation is going to be the planet's atmosphere. And so if you want to better understand what's happening with the outgoing radiation, therefore what's happening with the energy balance, and therefore what's happening with the planet's temperature, you need to take a closer look at what's happening in a planet's atmosphere. And this has been a question that scientists have thought about for a really long time. In the late 1600s, a French physicist named Aimé Mariette noticed that sunlight, or this incoming solar radiation, is able to easily pass through materials like glass, whereas other types of radiation, such as that emitted from a hot stove or is that emitted from a fire, are not able to pass through materials. So right away, or early on I should say, people were aware that sunlight has different properties than other types of radiation, and perhaps that might be important for bigger scale pictures, or bigger scale questions like what controls the climate. It was then in the first half of the 1800s that 2 more French physicists, including Joseph Fourier of the Fourier transform, did a similar calculation to what I showed earlier on, basically trying to show that the sun alone is not enough to explain how warm the Earth is, and there must be something else happening, namely the atmosphere must be interacting with this terrestrial radiation in order to keep the Earth at habitable temperatures. And they built on this idea initially presented by Aimé Mariette that sunlight is able to pass relatively easily through the atmosphere, just like it is for glass, whereas terrestrial radiation is being absorbed and then re-emitted by the atmosphere. So there's this key difference between these 2 types of radiation. However, at this point, it was not entirely clear why terrestrial radiation was interacting with the atmosphere in this way. We just knew that it was, and that it was keeping the Earth warm. Then in the mid-1800s, Eunice Newton Foote, an American scientist, discovered that certain gases, such as carbon dioxide or water vapor, have a warming effect. And this was a particularly notable discovery because the warming effect of gases such as CO2 is often attributed to an Irish scientist named John Tyndall. However, John Tyndall did his work 3 years after Eunice Newton Foote. And so it's a unfortunate but classic example of a woman making a very important scientific discovery only to have that discovery overshadowed by a male contemporary. But that all being said, John Tyndall did add one more piece to the puzzle. He specifically showed that gases such as CO2 and H2O provide this warming effect because the gases themselves are able to absorb and interact with the terrestrial radiation. And so let's go back to our rockstar model. Remember, we have this concept of energy balance, trying to track how much energy is coming in and out of a planet. And we know that if you have a planet with no atmosphere that's at a similar distance to the sun as the Earth is to the sun, you get a temperature of minus 18 degrees C. But let's consider a different picture now. Let's put an atmosphere around our planet that contains a bunch of greenhouse gases, like methane, like carbon dioxide. Again, we have our incoming solar radiation. And for now, let's keep the planet at minus 18 degrees C. This planet, like before, is going to be emitting outgoing radiation. However, some of this outgoing radiation is going to get eaten up by this greenhouse atmosphere, and therefore the energy going out to space is going to be less. This planet is no longer going to be in energy balance, and you're going to have more energy coming in than leaving the system. And what this means is that, anytime you have more energy coming in than going out, your system is going to warm up. And so the planet is going to warm up to a comfortable 15 degrees Celsius, which is very similar to the average temperature on Earth today, until energy balance is restored. And so this warming caused by this greenhouse gas atmosphere is what is known as the greenhouse effect. And I just want to emphasize that the greenhouse effect is not itself inherently a bad thing. It's the reason why Earth has habitable temperatures and the reason why we're all able to live here. But when you have too much of the greenhouse effect, then you can start getting warming that is beyond what the system has experienced for long time scales. And that's currently the situation we're in now. So finally, I just want to say that the strength of the greenhouse effect is very, quite well understood, and it's something that we've known about for a long time. So the metric that is commonly used in earth science is looking at the change in global mean surface temperature, so just the temperature averaged over the entire globe over a long period of time, with a doubling of CO2. In the late 1800s, Svante Arrhenius, who's a chemist, estimated that this value was roughly 5.5 degrees Celsius. More than a century later, after having huge increases in computing power and tons of fundamental breakthroughs on how we understand the Earth system, the best estimates from the Intergovernmental Panel on Climate Change put this number between 2 and 5 degrees Celsius. So I think it's kind of amazing that, using the rather simple methods of Arrhenius back in the late 1800s, he was able to get a pretty reasonable number for how sensitive the Earth is to warming. Granted, he was a little bit outside the bounds of the best estimate, but it just goes to show that we understand the warming effects of CO2 quite well, and it's quite clear that CO2 causes a lot of warming, or can cause a lot of warming on a planet. So with that, we'll take a closer look at our atmosphere and some of the other gases that are modifying the climate system.
Okay, awesome. Great. Well, thank you all. Again, my name is Eric, and I'm looking forward to talking a little bit more about what the atmosphere is actually made of. Why does it have these really interesting properties that Paul has already sort of alluded to that make it so our planet is habitable? For those of you who have a keen eye for geography, you'll probably recognize right there is Boston, Mass. We got north going that way. You could see Cape Cod jutting out into the Atlantic Ocean here. This is a beautiful image taken from the International Space Station from 2024, so a little over a year ago. It was in December. What I want you to notice specifically on this is how thin the atmosphere is. Look at the aspect ratios that we're dealing with here. We have this massive planet, and the atmosphere is just this little thin thing. And actually, a majority of what we're seeing here is the stratosphere, so parts of the atmosphere that we won't even really go into even if we're on a jet airliner. So anyways, the atmosphere is a very thin and small portion of the environment, but we rely on it for all of our lives, really. And so to talk a little bit more about what the atmosphere is made of, I want to do a little bit of call and response. Does anyone know what the dominant gas in the atmosphere is? Yell it out. Yeah. Nitrogen. Nitrogen, 78% of the atmosphere. Nitrogen, second most. Well, I spoiled it there. Third most, anyone? Argon, yes, argon. After that, carbon dioxide, about 0.4%, neon, and then a bunch of other things. I'm highlighting a few specific ones here, but the atmosphere is made up of a lot of different things, and in particular, some of these interact with radiation in a way that leads to a warming of the planet, others do not. The ones that, also it's worth noting, these percentages assume a dry atmosphere. So this is if you take all the water vapor and you squeegee it out, all you have is these things. Water vapor, depending on where you are in the planet, will be somewhere between 1% and 4%. If it was raining out today, it would be closer to that 4%. Otherwise, it would be on the lower end. And so you would just adjust all these percentages. But an important thing to note that Paul has alluded to is that some of these are greenhouse gases, which essentially means that they will interact with incoming or outgoing radiation. Well, they'll interact with outgoing radiation based on their molecular properties. And essentially, it allows them to absorb radiation coming out of the planet and then re-emit that according to the radiation that they receive in their temperature, leading to a warming of the planet. Now, also in the atmosphere, we have aerosols. Now, aerosols are just anything that is a solid or liquid particle that is suspended somewhere in the atmosphere. And these are typically classified by their size. So there's two different diameters that the size classifications will be based on. There's PM 2.5, which is just any sort of suspended particle that is smaller than 2.5 microns. And then there's PM 10, which is anything smaller than 10 microns. And these sizes correspond to the sort of effects that they can have on human health. So less than 2.5, they can get deep into the respiratory system and into the lungs and the cardiovascular system, whereas PM10 is less likely to get that deep, but still can be a irritant to breathing. And the constituents of this can include mineral dust, so things coming off of deserts, can include sea salt, so wind blowing across the surface of the ocean and then leading to the evasion of sea salt into the atmosphere, sulfates, nitrates, as well as black carbon, so soot, things burning, this can emit. And some of these aren't necessarily visible, but some of them are. So going back to some nice space station images, we can see these wildfires in Canada. So just to point here, this is the northern tip of Lake Superior, and we see all of these fires in central Canada. And the interesting thing that I want you to really pick off here is that, I mean, if you were on the ground, these would be massive, massive fires. But from a planetary standpoint, these are small, discrete points. These are very small, discrete sources. But the aerosols and the gases that these fires are emitting are then being wafted into the upper atmosphere and transported over great distances. You can see these large plumes extending well away from these sources. So the atmosphere is a very impressive thing in that sense, that these can really get around. So now to think a little bit more about what these particles will actually do to the climate system. This plot is one that's prepared by the Intergovernmental Panel on Climate Change. Paul has already alluded to this. This is a group of scientists that are largely working on a volunteer basis. This is something they do extra because they really care about it. And they synthesize all of the climate research knowledge from the last 5 or so years. And this has been done several times over the last few decades. So this is from the 6th Assessment Report. And what we're seeing here is the effective radiative forcing, basically the effective warming that anthropogenic and human activities have caused over the industrial time period. So 0 would be no change, and then 3, this is the total effect. And here, what they're doing is they're breaking it down by the actual constituent. So first we have CO2. We can see that a majority of that bar is contributed by CO2. There's also other greenhouse gases, including methane, nitrous oxide, halocarbons, so like things like chlorofluorocarbons, things that were regulated by the Montreal Protocol. Then we also have ozone, so surface level ozone. So there's another constituent that can lead to warming. And then stratospheric water vapor, so by some of our activities, including supersonic flight and rocket launches and things like that, we can perturb the amount of water vapor in the stratosphere, which leads to a warming, depending on where your water vapor is, can have an impact. And then albedo, so how we use the land. If we cut down forests and somehow make the surface brighter, that can lead to a slight cooling. If we put more soot particles on otherwise bright surfaces, we can lead to a warming. Contrails, that has a slight warming effect. Aerosols, so again, going back to that previous slide, things that are in the atmosphere, they can either warm or cool the atmosphere, but overall, they tend to cool, and that's broken down by their effect on the brightening of clouds, which is that lighter blue portion, as well as just direct effect of the color of aerosols and how those change the radiative balance of the planet. So that's that darker blue portion. An important thing to note here is solar. So change in solar output and its impact on the Earth over this period has a quantifiable but negligible effect on these changes in radiative forcing. So that's important to note. OK, so how has CO2 changed over time? This was something that a gentleman named Charles David Keeling was very interested in the mid-1950s. He came up with this really novel way of measuring the amount of CO2 in a bucket of atmosphere here. So he has what's called a flask. And he's collecting air here. And basically what happens is you open up this flask, you bring it back to the lab, and you're able to measure how much CO2 there is in the atmosphere. And so he was interested in doing this in a place where there weren't any sources nearby. Maybe he was also interested in a vacation, I'm not sure. But he decided to go to Hawaii. He went to the summit of Mauna Loa, which is a beautiful observatory where they still measure CO2 and a bunch of other trace gases to this day. And so we have a record dating back to 1958 of the concentration of CO2 at this location. And it looks like this. So for those with microphones, I'd like to have the opportunity for people to describe what they see in this plot. What do you notice, I guess? There's no wrong answers. This is. I'm seeing some fingers in the back. There's a. That's like a two-part answer there, but yes. Sure.
A superlinear increase.
Yes. Yes. So that's the dominant mode of variability. We have this increase that is in the rate of increase is increasing with time. So the amount of CO2 overall throughout this period is increasing. There's another mode of variability that's a little bit smaller. I saw someone in the back pointing. Does anyone want to see that? So we have this sawtooth almost, yeah? Does anyone know what that sawtooth could be? Winter. Seasons. Yeah, this is the planet breathing. This is the northern hemisphere breathing. During the summer, we have trees out. Our deciduous plants are actively photosynthesizing and pulling in carbon and leading to this drawdown. And in the winter, those leaves will fall off, and the underlying source will increase. And so respiration will dominate and lead to an increase in concentration. So with our observations that date back to 1960, we can see how these different components that Paul alluded to in our box model interact to lead to what we see in the climate system and the impacts that we see. So there is natural variability baked in, this nice sawtooth. And then there's this superlinear trend that is definitely dominating the entire record here. So with that, I will hand it over to Sandeep, who will talk a little bit more about these impacts.
Thank you. So how do we advance it?
Just the big green button.
OK. Yeah. So my colleagues have so far talked about how greenhouse gases are impacting the Earth's energy balance and how they have contributed to the modern warming. But to put modern warming into context, we need to look at how Earth's climate has been throughout the history. So to do that, we do not have like observations like how do we measure temperature currently. So we need to rely on some proxy observations. So one such observation, proxy way of observing Earth's temperature is tree rings. And like tree growth follows an annual cycle, like, and the growth is formed like rings along the trunk. So the outermost ring corresponds to the present day, and as we go towards the center, that corresponds to the earlier years. And during wet years, the rings are more wider, and during dry years, the rings are more narrow. So once we take a look at how the tree rings have been in the history, we can understand how the climate has been like during those years. So we get an estimate of how the local climate has been during those years by looking at the trees at a particular location. And once we compare those trees across different geographic locations, we can understand how the Earth's climate has been throughout those years. And trees, some trees exist for centuries. So tree rings are a proxy to understand how the climate has been over the past 1,000 years. And there is another source of observation, like these are ice cores. As ice deposits over Greenland or Antarctica, it also contains the air at that point in time. So when we dig deeper into the ice cores, we examine the ice layers, there is a trapped air inside which contains the information, the chemistry of the air which existed at that point in time. So using ice cores, we can understand how the climate has been over the last millions of years. And another source of observation is ocean sediment cores. So ocean sediments contain a lot of mud and microorganisms which contains the information regarding the chemistry and also the ocean temperature and how the carbon cycle has been over the last millions of years, like tens of millions of years. So using these kinds of observations, we can understand how the Earth's climate has been historically. So let's see how the Earth's climate has been millions of years ago with respect to today's temperature. So if you look at this, it shows how the Earth's temperature has been like from 70 millions of years ago with respect to today's temperature. If we see here, like Earth has been much warmer millions of years ago. If we see at about 50 millions of years ago, like the temperature of Earth is about 12 to 15 degrees warmer than what we are having today. And there was little permanent ice on the planet then. And since then, the climate has generally been cooling. And if you look at thousands of years ago, like this second plot shows how the Earth's temperature has been from 410,000 of years ago. And we can see a nice cycling pattern happening here, like cycling between the cold periods, which are ice ages, and warm periods, which are called as interglacials. Here we can also see the temperature and the carbon dioxide are following a good correlation here. The amount of carbon dioxide in the atmosphere and the temperature of the atmosphere, they follow a good correlation. And the last ice age ended about 10,000 years ago, and since then, the planet has generally been warming, and we are in a pleasant interglacial period currently. And when we look at like thousands of years, like 12,000 years ago, the temperature has reached a peak around 7,000 years ago, and then the temperature has generally been reducing. Like the temperature reduction has continued till the last 200 years, like about 200 years ago, and that is called as Little Ice Age. And after that, the Earth's temperature has been increasing. And like one important thing to note here is just the magnitude of the difference. Like millions of years ago, the magnitude, the change has been like -5 to like about 15 degrees, and then it's reduced like 2.5 to -7.5, and then currently the range is much smaller. But one important thing to note is how rapidly the current warming is going on. Yes, the rate of cooling has been slower, but the current rate of warming is much higher. And to put a quantity, a number to it, the warming over past century is like 1 degree centigrade per century, which is 16 times faster than the average rate of warming coming out of last ice age, which was 0.06 degrees per century. So climate change has not been new for Earth. The Earth has been changing, the climate has been changing. But what's new is the magnitude, the rate, the speed at which the Earth's climate has been warming currently. That is what is concerning. And also, like, we are moving out of the climate in which the current development or the infrastructure which we have built over the last 100 and 200 years, we are moving out of that climate, and which could cause issues. And also, this modern warming which we are talking about, my colleagues have talked about how greenhouse gases are impacting the modern warming. But are there other natural processes that could be causing the warming? Can this warming be attributed to different natural processes, or can it be just attributed to just the greenhouse gases that are being produced? Let's look at different natural processes and see how things are. So first thing we can look at is tectonic processes. And tectonic process is just how the continents move. This animation shows a very quick movement. This is happening in seconds, but this takes millions of years. The process is exceedingly slow. One interesting thing here is as continents move towards north, for example, as continents move towards North Pole, the ice sheet, the area of ice sheet increases. If the area of ice sheet increases, the Earth reflects more energy back, and the Earth becomes more cooler. That's how the climate could change, but this change happens exceedingly slow. Like the movements of these continents happen over like millions of years ago, and this is not really a reason why the climate change has happened over the last 100 or 200 years. And one more reason, like the reason for the Earth being warm, like the millions of years ago, there was no ice on the planet. That also is one of the reasons why the Earth has been much warmer, like millions of years ago, as there was no permanent ice. That is also one of the reasons. And looking at the next natural process, the ultimate source of energy for Earth is sun. If there is any difference in the output of the sun, did sun emit less energy or more energy, which warmed the climate of the Earth? But the observations over the past 100 or 200 years show that the sun's output hasn't changed much over the last 100 to 200 years, and the output of sun cannot be attributed to the modern warming. What if there are other processes? Like, say the sun's output hasn't changed. What if the distance between the Earth and sun has changed? What if the path of the Earth that is traversing around the sun is different? What if the Earth's tilt is different? Or what if the Earth is wobbling? There are 3 different motions of Earth that could contribute to the warming. Let's look at each motion. So Earth's path around the sun follows an elliptic orbit, but the shape of the orbit slightly changes in like 100,000 year cycles. So sometimes it's more elliptical, and sometimes the orbit is more cyclic. So this could be a reason for climate change, but still the cycles in which the change happens is 100,000s of years. So this is not really a reason why the modern warming is happening. What is this other change? So the Earth has a tilt, which is really the reason for why the seasons are happening. But the tilt currently is about 23.4 degrees. But the tilt changes between 22.1 and 24.5 degrees. And that happens across cycles of 41,000 years. So this also really not a reason, because this change hasn't happened over the last 100, 200 years. So this is also really not a reason why the current modern warming is happening. And the third motion is axial precession. This happens mainly because Earth is not a perfect sphere. Earth is slightly bulged around the equator, and because of that, the gravitational forces of sun and the moon on the Earth create an imbalance. So that causes the Earth to wobble slightly, and that wobble happens every 26,000 year cycles. This could change how seasons are, the intensity of the seasons. Sometimes the summer could be more intense, or the winter could be more intense. But this is not really a reason why the modern warming has occurred. So to summarize, the timeline of these variations are much larger and are responsible for ice ages, but these orbital variations cannot be the cause why modern warming is happening. And since these do not change much over a century, so these are not really the reason. So what about internal processes within the Earth? There are different processes. This process which I show here is El Nino Southern Oscillation. There are other processes like monsoons. Are they really the reason why the Earth could be warming? So these variations redistribute the heat within the Earth system, but they do not add energy to the Earth. So they cause short-term fluctuations, but do not create any long-term global energy balance. So the observations over the past millennium and even climate model simulations show that these internal variations of the climate are not really responsible for how the energy is gained by the Earth, or the cause for the modern warming. Now let's look at human influence, which are like greenhouse gases. Like since the Industrial Revolution, like human activities like fossil fuel burning or cement production or deforestation, they have increased atmospheric greenhouse gas concentrations. And these greenhouse gas concentration like reduce the infrared radiation going out, and they create an energy imbalance. So the timing and the magnitude of the observed warming align very well with the rising greenhouse gas concentrations. And when we try to simulate these changes, like simulate how the Earth's climate has been throughout the years, unless we add in the greenhouse gas forcing, we do not really observe how the climate has warmed over the past hundreds of years. So greenhouse gas provides a physical mechanism for sustained global house warming. And to summarize, so what is the cause? Like I wanted to summarize like 3 quick points. So the cause is adding greenhouse gases, especially carbon dioxide, traps outgoing infrared radiation and warms the planet. And what is the evidence for that? So evidence is direct measurements. We like Eric has showed us the Keeling curve, and there are paleoclimate records, ice core tree rings, and even observed warming patterns across atmosphere, ocean, and land. In the conclusion, the observed warming is real, it's quantified, and it's human caused. So what does the scientific consensus say? So this conclusion reflects like decades of independent academic research summarized by Intergovernmental Panel on Climate Change. In its 6th assessment report, it says, it is unequivocal that the human influence has warmed the atmosphere, ocean, and land. So yeah, this is what we wanted to talk about in Climate Science 101, and we'll dig into even more deeper details tomorrow in Climate Science 102, and we'll follow with climate policy after the coffee break. But if you have any questions, feel free to.
What is the reason for fluctuations, do you know? The heating and cooling of the Earth.
These
yeah,
ones?
That one.
Yeah, those are because of these orbital variations primarily. So these orbital variations, like, so the tilt causes how much heat the Earth is taking, like different parts of the Earth is taking. And the wobble also shows like at one point the northern hemisphere is facing the sun, when the Earth is closer to the sun, the northern hemisphere is facing, and other time the southern hemisphere is facing. This happens at like those tens of thousands of years. So those are the causes for those cold ages and interglacial periods.
Okay, I have 2 questions, Nick. You made mention about a glass metaphor that lets sun radiation in but doesn't let heat out. I wonder, in the case of the Earth, what would be that glass metaphor?
Yeah, it's a good question. Essentially what I was trying to say is the atmosphere is that. So sunlight is able to pass relatively easily through the atmosphere, but because we have these greenhouse gases like carbon dioxide in Earth's atmosphere, the radiation emitted from the Earth is not able to pass as easily through the atmosphere. Some of it still does get out to space, but it's impeded, whereas the energy from the sun is largely unobstructed as it comes in. Does that make sense?
It does. And I wonder if you can talk a little bit about ozone layer. I know that is something that I've heard in conversations. If you can speak to how does that come into play with the Earth is warming. Then I have one last question. I can drop the mic. You did mention the Earth warms by 2 to 5 degrees. I was curious if that is per year, if there is a metric.
Okay. I can tackle the first part if that's helpful.
Yeah. Sorry, yeah, do you want to go?
Yeah, I'll tackle the first part. So on the ozone depleting thing, I realized I went through this a little quick. If you could go to the radiative forcing plot. Yeah, this one. Okay, so here, what I'm showing there, so the third bar down, that is surface level ozone. So that's ozone that comes as a byproduct of air pollution at the surface. It's an atmosphere. It's a irritant to human health, and that's sort of what's being there. The one relevant to ozone is the next bar up, especially that that yellow portion of the bar. Those are halocarbons, essentially chlorofluorocarbons, hydrofluorocarbons. These are things that we use as refrigerants and as other sort of products that were formerly used in aerosol cans, for instance, propellants for those. And those are known to deplete ozone in the stratosphere. When they're at the surface, they're not harmful. However, over decades, they can end up in the stratosphere where they can deplete ozone there. So that would be the connection between warming. So it happens to be that those same compounds that deplete ozone are also greenhouse gases on their own. So actually, by eliminating those compounds, we've actually made a little bit of progress in terms of climate adaptation and mitigation.
And then just really quick, to answer your last question, so this 2 to 5 degree estimate is the way this number, people needed a way to quantify how strong the greenhouse gas effect is. And so The way that they chose to do that is somewhat arbitrary, but they double CO2 and then they let the climate come to a new long-term equilibrium. So the 2 to 5 degree number is the change in global mean temperature after the climate has come to equilibrium after the CO2 is doubled. So you can think of this as like 2 to 5 degrees over, say, 1,000 years, if you double your CO2 from a reference value. Does that make sense? Or?
So thank you very much. So there are ongoing discussion about the geoengineering, which is like spreading small particles in the atmosphere to reduce the global warming. So do you think this can affect in a global scale, or it's just a limited scale problem or something?
Yeah, I guess I can try and tackle that one first, and others can jump in as needed. I would say it's one of those things where, as a back of the envelope, it would make sense, right? You could do a back of the envelope calculation and say, yeah, if I did that, then I could change the radiative balance of the planet. But the real problems come in the cascading effects that has. So one of the typical solutions would be sulfide aerosol particles in the upper atmosphere. Okay, well, that's fine when it's there. What happens when it falls out of the atmosphere? Does it become a problem for ecosystems? Does it become a problem for humans? And there's a logistical question, too. How do you put that much stuff into the atmosphere? It would be one of the largest undertakings in all of human history in terms of an engineering solution. So it's, again, a back of the envelope, yes, you can write an equation that says, well, yeah, you could do that. But logistically and ethically, there's huge questions to be answered that require a lot more scientific study. And there's a lot probably simpler and easier ways of getting at the solution that you would want than going that route, would be my argument. Happy to talk more.
And as a shameless plug for tomorrow, we'll be talking about impacts of climate change and some of these cascading effects that Eric just referenced.
Thank you. Hi, just on that slide, so when you say doubling of CO2, what base level are we talking about?
I believe the reference level is the pre-industrial CO2 concentration. I don't remember what that number is off the top of my head, but it's something like 280, it's 273 ppm. Okay.
And where are we now in relation?
Oh, we're at like 440 right now.
Sorry, 440 out of the...
Sorry, so the baseline is 273 parts per million of CO2, and current CO2 concentrations in the atmosphere are like 440.
So we have more than. And before humans, we did see kind of CO2 variation. So what caused these CO2 variations?
Not exactly sure.
Yeah, so that's like generally an open question in science, I would say. The ocean on long time scales can store and release a lot of carbon. There's more carbon in the ocean than there's, I don't know, 38,000 petagrams of carbon in the ocean, whereas there's like 600 petagrams in the atmosphere or something. So there's orders of magnitude more carbon in the ocean than there is in the atmosphere. The timescales on which processes operate in the ocean are generally pretty slow. So for human relevant timescales, the ocean is a carbon storage. From a natural perspective, isn't the most relevant, but when you start getting out into longer geological timescales, the ocean can start releasing a lot of carbon or taking up a lot of carbon, and that can change how much carbon is in the atmosphere. You can also get major volcanic eruptions that can influence the, and not just like a one-off event, but like there are periods in Earth history that have more volcanic activity than other times, and this can lead to changes in the CO2 in the atmosphere. The position of the continents can also influence how much carbon you have in the atmosphere. So it kind of depends where you're looking, but there's a whole host of natural processes that can modify carbon in the atmosphere. Just all of those happen on much slower timescales than we would like for modifying how much carbon we have now. There's a question over here.
Does deforestation have a measurable effect on the seasonal change in CO2? Because I know that the Amazon, for example, has experienced significant deforestation recently. And I'm wondering how much of carbon storage is attributed to forests and trees, and like how much of an effect do we see due to deforestation there?
I can try and address that. I would say, in terms of the seasonality, it depends on where you were to do it. So in the Amazon, you're in the tropics, and so the trees there have less of a seasonality than we would have in the northern hemisphere in terms of their productivity. They're productive most of the time. Yeah, in terms of vegetation as a solution to human-caused climate change, you can get sort of a back-of-the-envelope sense of how effective that would be simply by looking at, like, for instance, that Keeling curve, right? So we saw that dominant mode of variability where we saw, again, that almost exponential sort of growth in the concentration of CO2, and we saw the effect of pretty much all of the northern hemisphere seasonal vegetation working together at once, underlying that. And it's just a little sawtooth pattern there. So trees are a good thing for a variety of reasons, but there won't be the silver bullet to fix that overarching trend. There's actually a lot of interesting research in terms of where your trees are, in terms of the relative effect of how much carbon you're pulling out because you're a tree, and the competing effect of how much you're warming the surface simply because you're a dark tree that's absorbing more sunlight. So this is referred to as the biogeophysical versus the biogeochemical effect of vegetation, which I'm happy to talk about more during the coffee break. It's really a fascinating area of research, but great question.
Just as Sandeep summarized, we have a clear picture that how humans are impacting the climate change today. Question for you who are scientists, is there still debate of how we are influenced, or people are still in denial? How is this discussion among the scientists today, 2026?
To go for it.
I would say among the vast majority of people who work in the earth science, questions regarding whether or not CO2 causes warming it's not up for debate at all. There's a handful of like the extremely small minority who at this point have largely kind of been, who I would say honestly are not as taken as seriously for having such views, think that might not be the case, but the vast majority of scientists agree with the basic physics that CO2 causes warming, and yeah, does that make sense?
Just to piggyback off of that too, like scientists as a profession, we should be arguing with one another to an extent to understand sort of what the effects are, and our arguments still exist. For instance, that line there. Our best estimates are somewhere between 2 and 5. We disagree on the exact number, but that number is going in the same direction, right? So the impacts are the same. It's more so a discussion about how bad will it be, kind of
thing. Could you bring up again the graph on the 100,000-year time scale?
1 sec. The Ice Age one?
Yeah. So it looks to me like, tell me how my interpretation of graph reading is, that in the middle graph, the cycle looks like first the temperature goes up, then CO2 starts to follow it up, then CO2 starts to come down, then temperature starts to come down. So am I reading that right? Is that a set of feedback loops that saturate? Like what's the physics there?
I can say, so in this particular graph, the way this data is plotted, that's the case that one appears to lead the other. I would say the thing that's not being shown on this data is when you're looking at a climate proxy from hundreds of thousands of years ago, the error bars on the dating for that are going to be quite large. And so doing any sort of lead lag analysis with CO2 and say temperature for data that's 100+ thousand years old is challenging. And I would not put too much stock into whether, this curve peaks, what, a few thousand years before that curve. That's going to be a hard thing to make. And if you went, the other thing too is these data come from, in this case, most likely come from sediment cores that are taken at discrete locations in the ocean. And so the timing of events from one sediment core to the next can be impacted by a whole host of things. And so you should just always be aware that when you're working with or looking at paleoclimate data, there's just a lot of uncertainty. That one sediment core may have had this event happen at this particular date. The other sediment core could have had the same event happen 1,000 years later or earlier, and you kind of just have to roll with the fact that it's uncertain. People are trying to constrain the uncertainty as best they can, but the ultimate fact of the matter is we're looking at data that's really old. So does that make sense? I know it's not a super satisfying answer, but I think that's kind of the current state of thinking about things.
Okay, thanks.
One just super quick question, which you may or may not be able to speak of. Last month, I remember you mentioned the Hawaii Observatory. I remember last month hearing about the National Center for Atmospheric Research, that it's going to be closed, and I'm wondering from your perspective, like, I haven't heard anything since. Like, what is the fallout looking like at the moment? Are there contingencies? Are there international partnerships? Like, what are, from your own perspectives, what is the concern at the moment, and maybe hope, if any?
I think at this point, we do not have enough information. I think we are just reading what you are reading, and we are also looking to see what's coming out from the current administration, to be honest.
I think the hope for all of us is that it doesn't actually close and that was just a threat, but I personally have not heard anything one way or the other since that announcement.
Yeah. Chris might have more info.
Am I live? Cool. Small comment to add on that. There was a recent bipartisan bill introduced to save NCAR and make sure that it does not get dismantled. So there is an active effort currently to prevent that from happening. So if you are politically inclined, call your legislators and get them to sign on to that bill.
Any other questions or? Okay. If not, we'll be around during the break, so if you have things you want to talk about, feel free to come find us. And if not, and then we'll have a roughly 15-20-minute break, and then we'll come back for the second part of this session on the fundamentals of climate policy. Awesome. So thank you all.